In this lesson, we'll talk about rational exponents. Rational exponents are used as alternative notation to radical notation. Particularly, nth radical of x means the same as x raised to the exponent 1 over n. So the index of the radical is the same as denominator of the rational exponent. Generally, if we have nth degree radical from x to the m, this exponent m could be written outside of the radical, and then since nth radical of x is the same as x to the 1 over n, since we are taking everything to m, we're going to multiply those exponents, so overall we have x to the m over n. Okay, so let's remember that the exponent m becomes the numerator and the index of the radical n becomes the denominator of the rational exponent. So any radical expression can be actually written in exponential form. These two notations are equivalent. However, since it's easier for us to use exponential rules, sometimes it's beneficial to rewrite the expression in radical form into the expression in exponential form, then perform the desired calculations and finally come back to the radical form. We'll see how this works in examples to follow. For now, let's focus on the fact that the index of the radical becomes the denominator of the rational exponent. That will be useful to know when we need to convert our expression from radical form to exponential or the other way around. Okay, we have a bunch of exercises to go through. In the first example, we want to change from radical to exponential form or from exponential to radical form, whichever applies, and then simplify if possible. Okay, let's practice. Root of 5, since square root has invisible index 2, we can rewrite this as 5 to the exponent 1/2. Now, cubic root of 2, that's the same as 2 to the exponent, since 3 goes to the denominator, so it's 1/3, isn't it? And the following radical, let's keep the base 3. Now, the exponent 2 becomes the numerator of our future fractional exponent, and the index of the radical, which is 5, travels to the denominator. So we have really 3 to the 2/5. Okay, let's try the next example. 4th degree root of 25. First of all, let's rewrite 25 as a power of prime number. This is really 5 square. So we have 4th degree root of 5 square. And then we can use this property. Keep the exponent 2 in the numerator of the fractional exponent and the index of the radical in the denominator. Can we simplify this any further? Well, yes, we can, because now our exponent is 2/4, which simplifies to 1/2. So we really have 5 to the 1/2. Notice that that was very useful to actually simplify this 4th degree root of 25. We haven't been asked for it yet, but we could leave this answer either in exponential form as desired in this question, or rewrite it back to the radical form, but the radical is already simplified. You see, this is the same as square root of 5. So 4th degree root of 25 is the same as square root of 5. However, we are not asked for it in this example. The next question, we have square root of 16, which is 4, and then we have square root of x to the 4. Well, do we know how much is square root of x to the 4? If we are not quite sure, we can rewrite this in exponential form. So we can write x to the 4/2, isn't it? 4/2. But you see, 4 divided by 2 is actually 2. So in the next step, we can write just x squared. And the following variable, y, it was raised to the power 2, but since the root translates into denominator 2, then we actually have y to the 1. Okay, let's simplify this. We have 4x to the 2 and y to the 1. Wow, that's great. We actually simplified this radical, and the result is just one single term with no fractional exponents anymore. I want you to observe one more time what's happening to those powers of variables. In order to simplify the root, what we've done, we actually divided 4 by 2, isn't it? So we could write this final answer at once. It's enough to perform this division on exponential level in our minds. So 4 divided by 2 is 2, and 2 divided by this invisible 2 is 1. Okay, let's keep this in mind. It will be useful in the future. Next example. Let's rewrite this in exponential form. Okay, we need to deliver this exponent 5 to both variables, to x and to y squared. If I deliver the 5 to the x, I have x to the 5 over, and this is my denominator, 3, right? So x to the 5/3. Now, to deliver the 5 to the y squared, since this is power to the power, I'm supposed to multiply those exponents, right? So I end up with y to the 2 times 5 is 10, again over 3 because of this root. Great, that's exponential form. What do we have in the next example? This time we start with the exponential form, so let's convert it back to the radical form. Remember, denominator of the fractional exponent becomes the index of the radical. So we deal with 7th degree radical of x squared, just like that. Next, we have 3x to the negative fractional exponent. So first of all, let's perform this negative. Remember, if we raise something to a negative exponent, we need to take reciprocal of the base. So the 3x actually travels to the denominator. It will be 3x in a bracket to the 2/5. Okay, so let's rewrite this fractional exponent in a radical form. That would become 1 over 5th degree radical, because of this denominator 5, of 3x squared. But notice that writing 3x squared like this wouldn't be correct, wouldn't it? Why? Because this exponent 2 refers only to the x, it does not refer to 3, but we're supposed to raise the whole 3x to the square, so we are obligated to use a bracket here. It must be written inside the bracket. Okay, so that's the radical form. Let's see if you can rewrite the next example in a radical form by yourself. Okay, remember that the exponent -1/2 refers just to the x because we don't have any bracket here. So the 3 is with the exponent 1, which means 3 will stay in the numerator. However, x, because of this negative, travels to the denominator, and now it's raised to the 1/2. Okay, in a radical form, it will be written 3 over square root of x. Did you get the same answer? I hope you did. And the last example, the whole bracket to the 2/3. This is positive exponent, so we keep everything in the numerator. Since the denominator of our exponent is 3, we start writing cubic root of everything to the square. So bracket x plus 2y square. Here we go. In the second example, we want to evaluate the following expressions. My suggestion in this type of problems would be to rewrite the bases that we deal with as powers of prime numbers. Obviously, if possible. Let's see. When we look at 8, we can most likely recognize that that's a perfect cube number. It is actually 2 cubed, isn't it? And then, if we raise this to -1/3, it's enough to perform the multiplication on exponential level. Remember, power to the power means multiply exponents. So this 3 will cancel that 3, and we end up with 2 to the -1, which is 1/2. Take the reciprocal of 2. So that's great. Changing the base into power of prime numbers will often make your calculations a lot easier. Let's see the next example. We need to copy the minus, and then 64 was taken to 2/3. But what if I will change 64 into power of a prime number? This is 2 to certain power. Let's count on your fingers. 2 times 2 is 4, times 2 is 8, times 2 16, times 2 32, and times 2 64. So how many 2's did we use? 6 of them. 64 is 2 to the 6. And then when we raise everything to 2/3, when multiplying exponents, we notice that the 6 and 3 can be reduced. This is 1 and this is 2. That makes it a lot easier because now we don't need to deal with any radicals. There is no denominator on exponential level. Okay, let's copy our negative, and then we have 2 to the 2 times 2 is 4. So altogether it's negative 16. 2 to the 4 is 16, right? Okay, let's see if you can do the same by yourself. Let's check it. We have negative 125. That's the same as negative 5 to the 3. Notice that negative 5 to the 3 can also be written as negative 5 in a bracket to the 3 because negative to the odd power becomes negative. So we end up with the same answer so far. And then everything needs to be raised to negative 1/3. Okay, so now we're supposed to multiply those two exponents, which causes that the 3 will be cancelled and we don't have to deal with cubic root anymore, right? So we have negative 5 bracket to the negative 1. But this outside exponent negative 1 causes that we need to take reciprocal of the base. So it's 1 over negative 5 or negative 1/5, which means the same. Did you get this answer by yourself? Great. Let's try the next example. 16 over 81 to certain negative fractional exponent, which really indicates a fourth degree radical. But let's see if we can evaluate this expression without going into radicals. First of all, change 16 into power of 2. That's 2 to the 4. Change 81 into power of 3. That's really 3 to the 4, isn't it? And then let's raise everything to the negative 3/4. Now, notice that since the two exponents for the numerator and denominator are the same, we could actually write this as 2/3 as a base and then raise to the 4. After that, we need to raise everything to the negative 3/4. That helps because when we multiply exponents, the 4 will be reduced, which makes it a lot easier. So we end up with 2/3 to the negative 3. And now to perform this negative on exponential level, we're going to flip the base. So we really end up with 3/2 to the 3. Finally, we can deliver the exponent 3. So 3 to the 3 is 27 and 2 to the 3 is 8. So we end up with 27/8 overall. Let's see what do we have in the next example. Here we need to simplify radicals. Also, we assume that all variables are positive. That's useful to know because remember, when we've been working with even degree radicals, we've been always protecting the answer to end up with a positive value. Since all the variables are positive, we don't have to watch this absolute value problem, right? Also, leave your answer in a simplified radical form. We always need to read carefully the instruction. So we need to leave our answer in simplified radical form. However, there's a little hint. Convert to rational exponents first. Why? Well, because it's a lot easier to work with exponents than with radicals. Let's do it. Square root of 5 to the 10 is the same as 5 to the 10 over 2. It's enough to reduce this fraction. 10 divided by 2 is 5. So overall we have 5 to the 5. We don't have radical anymore. Since 5 to the 5 is a very large number, we don't really need to evaluate this. We are not after the large numerical answers. Powers of prime numbers are fine to leave as our final answer. Okay, let's see the next example. If we want to rewrite this radical in exponential form, that will be x to the 18 over 6. And again, let's perform this division. It becomes x to the 3. Very nice answer, no radical anymore. Next, here we have y to the 2/4. Let's reduce our fraction. That becomes y to the 1/2. As soon as we see a fractional exponent, this is really hidden radical, so we need to go back to the radical form. It becomes square root of y, simplified radical form. That's great. Next, square root of a times cubic root of a squared. We can't really multiply these two roots because they are of different indexes. They are totally different items. The only way that we can actually perform this multiplication is by converting each expression to the exponential form. So root a is the same as a to 1/2. Cubic root of a squared is the same as a to the 2/3. And then, since we know what to do when we multiply powers with the same basis, what do? We add exponents. So we keep the base and we add exponents. But since these two fractions have different denominators, to add them, we need to convert both of them to the common denominator, which is 6. Okay, to get 6 in this denominator, we need to multiply by 3. But then we multiply the numerator by 3 as well. And to get 6 in the second denominator, we multiply the bottom and the top by 2. So overall, we have 3 from the first fraction and 4 from the second fraction. Okay, let's carry on. We end up with a to the 7/6. This is already good, but it's exponential form. Let's convert it back to the radical form. That becomes 6th-degree root of a to the 7. Is it anything else that we can do here? Well, yes, it is. Remember, 6th-degree root really means that anytime we have 6 of the same factors, we can take one representant out of such a group outside of the radical. So in this case, let's rewrite it again so everybody can see it clearly. A to the 7 is the same as a, 6 of them, and times another a 7th one. From this group of 6 a's, we can pull out a representant, 1a, in front of the 6th-degree root. What's left is the other a. So the final answer is a 6th-degree root of a. That's the simplified radical form. Let's see the next example. This time we want to simplify nested roots, square root of a cubic root of 2. In such situation, let's rewrite our radicals in exponential form starting from the inner one first. So cubic root of 2, that's the same as 2 to the 1/3, isn't it? But then the outside root, square root, tells me whatever I had inside, I need to raise to 1/2. Okay, so now we know what to do, isn't it? Because it's power to the power, so we multiply exponents. Therefore, the final answer in exponential form would be 2 to the 1/6. But we want to leave the answer in simplified radical form, so let's rewrite it back to the radical form. It is 6th-degree root from 2. Okay, and the last example from this bunch, we have a division of two different types of roots. We can't really divide, we can't cancel those x's, because they are under different exponents really. So what we need to do is convert to the exponential form. The numerator can be written as x to the 1/4 and the denominator x to the 1/5. And now we know what to do. When we divide powers with the same basis, we subtract exponents. So keep the base x, and then we deal with 1/4 minus 1/5. So this question translates into operations on fractions. Okay, that's x to the, let's keep common denominator 20. And now to make the new denominator 20, we need to multiply the first fraction, top and the bottom, by 5. And the second fraction, top and the bottom, by 4. So we end up with 5 minus 4, which really is 1/20. Okay, we have x to the 1/20. And then to convert to the radical form, it becomes radical of the grade 20 out of x. That's all. In the next example, we need to simplify various expressions with fractional exponents. Again, we assume that all variables are positive, so we don't have to worry about absolute value in the end, and we need to leave the answer with positive exponents only. So in the first example, we need to multiply powers with the same bases. Therefore, we keep the base and add exponents as they are. We predict that we need common denominator for any addition or subtraction of fractions, isn't it? So the common denominator here will be 20. And then how do we change the first fraction? We multiply top and the bottom by 4. So 4 times 2 will be 8. And then plus, because of multiplication of powers, however, the number it's negative, right? So when we multiply top and the bottom by 5 to make denominator 20, we end up with negative 3 times 5 is negative 15. So overall it's like 8 minus 15, which is x to the negative 7 20s. Since we want to leave the answer with positive exponents, let's perform this negative by moving the whole expression to the denominator. So we have 1 over x to the 7 20s. And since we don't really have any indication whether to leave the answer in exponential form or in a radical form, we could leave the answer as it is, or equivalently, we could say 1 over 20-degree root from x to the 7. So either like this or like that, both are fine. In the next example, we have division and multiplication of powers with the same bases. So the whole question really translates in operations on fractions. So we keep the base, and then we keep the exponent from the numerator 1/3, but then we change division into subtraction of everything what's here on the exponential level. So we need to place a bracket. Remember, if we subtract and there is more than one term coming in, then the bracket is essential. In the denominator, since we multiplied powers, we are adding those exponents. So we have negative 1/4 plus 2/3. Okay, this negative is because of the division of powers, and that negative is because the number was negative. Okay, let's perform those operations on exponential level. So common denominator would be 12. And then 1/3 becomes 4/12. Next, these two negatives make it plus. 1/4 becomes 3/12. And remember, this minus is going to be distributed, so it's going to switch this plus into another minus, right? Okay, 2/3 becomes how many 12s? 4 times 2, 8 12s. Let's carry on. The base a to the exponent 4 plus 3 is 7 minus 8 is negative 1/12. Okay, so to perform this negative in exponential level, we are moving a to the denominator, and then it becomes positive exponent, right? And the numerator is 1. Okay, now we can leave the answer this way, or we can change it into radical form. So that will be 1 over 12-degree radical of a. Either like this or like that, both answers are fine. Okay, let's see example C. Here we have so many powers and everything is raised to another power. What we can do, we can clean up whatever is inside the bracket and then deliver the negative 2. Or we could deliver the negative 2 and then simplify. Both ways are really fine. In this case, since we have fractional exponents that at least some of them can be reduced when multiplied by negative 2, maybe let's deliver this exponent to every single factor inside the bracket, because that will simplify those fractional exponents quite a bit. Okay, p to the negative 1/4 raised to the negative 2, we multiply exponents, so it becomes p to the 2/4, which is 1/2. Positive 1/2, right? Then q to the negative 3/2 times negative 2 is actually just 3 over, and then 3 to the negative 1 times negative 2 is 3 to the 2. P to the negative 2 times another negative 2, that becomes p to the 4, and q to the -3/2 times -2, that becomes positive, and the 2 is cancelled, so it's just 3. That makes it a lot simpler, isn't it? Now, as you can see, we can reduce these two cubes of q, right? Because they are the same. And finally, we just need to combine the p's. Since we have p to the 1/2 in the numerator, if we move this p to the 1/2 to the denominator, leaving numerator as 1, we have 3 squared, and then p to the -1/2, and then p to the 4. So now to combine these two p's, we need to add exponents, right? So the answer would be 1 over, instead of 3 squared, we can write 9, and then p to the 4 minus 1/2 is 3.5, but 3.5 can be written as 7/2. And that's good. This is already a good answer. If we want to leave the answer in a radical form, it will be 1 over 9 square root of p to the 7. And then, well, we could actually do one more step, because we could simplify the root of p to the 7. Since under square root we have 7 p's, we can ask ourselves, how many pairs of p's do we have? Well, the same many times the 2 goes into 7. So see, we really divide the 7 by this invisible 2, and the quotient, which is 3, that's the exponent of p that goes out of the radical. So we have 1 over 9, and then p to the 3, because on the side 7 divided by 2 is 3, remainder 1. So see, if we look at the exponential level, the quotient 3, that's the power that goes out of the radical, and what stays under is the remainder 1. So p to the 1 stays under. Okay, that will be the simplified radical form. Finally, let's perform this multiplication. It works the same way as regular multiplication of polynomials by a monomial. So we need to distribute this monomial, 7y to the 8/5, inside the bracket. So multiply by the first term and then multiply by the second term. Okay, one step at a time. 7 times y to the 8/5 times y to the -8/5. So we have 7 for sure, and then it's y to the 8/5 minus 8/5. Well, it's 0. That's great. That makes it a lot easier. Then we rewrite the minus, and again multiply 7 times 3 is 21, and combine the exponents of y. 8/5 minus 3/5. Well, it's like 5/5. But how much is 5/5? It's 1. Okay, that makes it a lot simpler. Y to the 0 is 1, so we really have just 7, and then minus 21y. Just a nice polynomial, no more fractions, so that was really worth to do, isn't it? One more example. Let's simplify radical expressions like this. Again, assume all variables are positive. Leave your answer in a simplified exponential form this time. Okay, let's convert everything into exponential form, starting from the most inner radical. So, 4th degree radical of x is the same as x to the 1/4. Then if we apply cubic radical of it, this part, then we need to raise everything to the 1/3. And finally, to apply square root of everything, then we raise everything to 1/2. So overall, this question is not difficult at all, because what we do, we just multiply all those exponents. So we end up with x to the 1/24, or 24th degree root of x. That would mean the same. However, we're supposed to leave the answer in exponential form, so that's the final answer. Let's see the next question. 4th degree root of x to the 5. That's the same as x to the 5/4. And then we divide it by x to the 2/3. Okay, now we need to divide these two powers, so we need to perform subtraction on exponential level, keep the x, and subtract, meaning the denominator must be common, which is 12 in this case, and then to make it 12 we multiply the top fraction by 3 in the top and the bottom, and the bottom fraction by 4, top and the bottom. Okay, so we end up with 15 minus 8 equals x to the 7/12. And that's where we stop, because we end up with simplified exponential form as needed. Finally, the last example asks us to find the domain of this particular function. Remember that anytime we see a fractional exponent, that's a hidden radical, so we need to take care of radicands. Also, anytime we see a negative exponent, that's a hidden denominator. We need to take care of denominators for domain, isn't it? So the first thing that I would suggest is to rewrite this function in radical form. That means instead of 1/2, let's write a radical, square root of x plus 1. And then because of this negative, we place this bracket in the denominator, so it's over x minus 2 to the 1/3, but that means cubic root of x minus 2. If we see our function this way, it's easier to detect what are the conditions to satisfy by the domain. So, since the function has denominator, we need to watch denominator not to become 0, right? So the conditions to protect or to check are as follows. Our denominator can't be 0, which means x minus 2 must be different than 0. That's the first condition that we need to keep. Also, meaning and, our radicand for even degree radical must be bigger equal 0. So x plus 1 must be bigger equal 0. And then let's solve these two inequalities and figure out what's the overall domain. Okay, x minus 2 is different than 0. That means that x must be different than 2. That's reasonably easy. Now, second inequality, x must be bigger equal, move the 1 to the other side, -1. And the connecting word between these two conditions is and. Okay, let's draw these conditions on the number line so we can see where's our domain. X is bigger equal -1. If -1 it's, let's say, here, x bigger equal -1, that's this set. Okay, everything here. Also, x must be different than 2. So if 2 is, let's say, here, we need to exclude this point. So we need to make a break in this set. And the overall domain will be everything starting from -1 until 2, all these numbers. Then skip the 2 and go farther from 2 to the infinity, these numbers. Okay, we are ready to give the final answer. Domain of the function f is, and then we need to list two intervals connected by the union sign, right? So starting with -1, inclusive. -1 can be taken, that's not a problem. We can have 0 in the numerator. Going until 2, exclusive. 2 is not taken. Skipping the 2 and then from 2 to the infinity. Okay, that's our domain.